Okay, so Fermat's theorem states that for a function over the interval a to b on the reals is differentiable at some c, if the function has a local maximum or minimum at c, then the derivative at c has to be equal to 0. So now let's recall the definition of being differentiable at c, which states that f prime of c is equal to the limit as x approaches c of f of x minus f of c over x minus c. And the definition of a local maximum states that there exists a delta greater than 0, such that for all x in this here, c minus delta and c plus delta, x minus c in the absolute value is less than delta implies f of x is less than or equal to f of c. Okay, now there's a similar case for the local minimum, but we'll get to that in a minute. So first let's do the proof for the maximum side. Okay, so given the above, f of x is less than or equal to f of c, we can rearrange this to say f of x minus f of c is less than or equal to 0. Okay, so if we look at this case here, if c is less than x, which is less than c plus delta, this implies that 0 is less than x minus c, which is less than c plus delta. Okay, and given this fact above, if we have our derivative here, f of c would have to be, the numerator would have to be less than or equal to 0 from this fact, and the denominator would be greater than 0, okay, which is x minus c here. So this would imply that the derivative itself would be less than or equal to 0, okay? Now for the other case, if we have c minus delta being less than y being less than c, this will imply that c minus delta is less than y minus c, which is less than 0. Now, given this above fact as well, the derivative, f of c, the numerator again will be less than or equal to 0, but the denominator here will have to be less than 0, okay, from this condition. So the derivative overall will have to be greater than or equal to 0 then, just intuitively. Now, as a limit is unique, limits from both sides must both be the same, right? Now, the only case where a number is less than or equal to 0 and greater than or equal to 0 would be when f of c is equal to 0. Okay? So that's our maximum case. Now, if we do our minimum case, the definition of a local minimum is similar to this one, but we say for all delta greater than 0, such that for all x on the bound c minus delta, c plus delta, this implies that f of x is greater than or equal to f of c. Now, if we do a similar thing to above here, this can be rearranged to give us f of x minus f of c is greater than or equal to 0. Okay? So now we'll separate this into two cases again. So if c is less than x, which is less than c plus delta, this gives us 0 is less than x minus c, which is less than c plus delta. And given this above fact, the derivative, the numerator, will have to be greater than or equal to 0, and the denominator will have to be greater than 0, okay? Which will give us an overall derivative which is greater than or equal to 0. Now for the next case, if c minus delta is less than y, which is less than c, this implies that c minus delta is less than y minus c, which is less than 0. And given the above case, the derivative will the numerator will be greater than or equal to 0, but the denominator will be less than 0. And intuitively, this means that the derivative itself will have to be less than or equal to 0. And again, the limits of both sides they must be equal as they're unique. And the only case where this holds, greater than or equal to 0 and less than or equal to 0, is where f of c is equal to 0 itself. And that's our proof for both cases.